Hey everybody, I'm Jesse Wilson from Square, and I'm here to ramble on about JNI for a little bit. Um, and this isn't the JNI talk you were expecting. I'm really going to talk about why and how it works, more than I'm going to talk about any of the implementation details, because the implementation details are just incredibly boring. All right, or at least the API details. So I want to start out by talking about Java, and so we just all watched a talk about Kotlin, and so it's going to feel a little awkward for me to talk about how great Java is, but I'll do it. Um, so Java is this like wonderful productive language. The reason that it was chosen for Android was because it's so productive. There's lots of great libraries. You can do lots and lots of things in Java, and despite the fact that it's such a high level system, it's also a fast enough programming language. You talk about programming languages and how when you go to deploy them, you have problems. Java's generally like fast enough, and generally people who don't have performance problems with Java. And then just like the productivity, Java scales up to hundreds of people on hundreds of developer teams. Yeah, so I'm a big fan. Um, and Java, as we know, all runs on the Java virtual machine. And the Java virtual machine is this expensive, fancy technology that's Sun and Oracle have been developing. Literally hundreds of man years worth of investment into this application. And what it does is it takes the Java programming language and it gives you an architecture neutral place to deploy. So that means you can write your Java on a x86 Mac and then deploy it on an ARM Linux Android phone. It's also garbage collected, and it's also fast. I think this is like sort of a theme. And I wanted to say that Java is just-in-time compiled and interpreted on the JVM. And Android developers are now working on ART, which is the Android runtime. It's basically an alternative idea at solving the same sorts of problems. Also architecture neutral, also garbage collected, also fast. And it has one extra feature, which is it is available including ahead of time compilation, just in time compilation, and it has an interpreter in it. So when you're writing your code for your Android app and you deploy it on the device, that code sort of runs in all sorts of different modes simultaneously and cooperatively. When you upgrade your Android phone and you see that it like is re-optimizing the apps, what that's doing is it's actually doing the ahead of time compilation again. And so you're actually like rebuilding your apps for your device every time you install them and every time you update your OS. All right, so I'm going to talk more about architecture neutrality. Um, there are some popular architectures. These things are sort of like trendy. Um, right now, ARM is really hot. 10 years ago, it was Power. And we're hoping that like 10 years from now, it'll be maybe something new. Um, And the reason that we want to be architecture neutral is because it means that the operations of being application developers is much easier. When you ship one app, and you don't have to worry about whether you're writing your app for uh, Android for this platform, Android for that platform. It doesn't really matter what the CPUs are. You can write your same Android app and target that crazy. Was it a crazy Lenovo device that had an x86 processor in it? Um, and even just things like you build your app, you can test it on an x86 emulator and have a very high degree of confidence that it's going to work on your ARM device. And a thing that's important here is that the neutral architecture is both the CPU architecture, x86 ARM, and also the operating system. So you take Linux x86 and Mac x86, and it's actually slightly different in terms of what the binaries look like on sort of a native system. So let's look at like our classic pre-Java application architecture. We have our x86 computer or our ARM computer, we have our ARM operating system, and we have our ARM application. And these things all have to agree or nothing works. What Java gives us is it gives us this extra layer where suddenly the virtual machine is architecture specific, but the application doesn't need to be. So that's architecture neutral. Um, so you're writing your application code, and your application is doing lots of things. Maybe your application is saying like, hey, hey VM, I'd like to allocate an object. And so your application code is running in that top orange layer, and it calls into the JVM. The JVM goes and finds some memory and gives it back to you. And so there's this like sort of like call process between these layers. And this call process exists sort of repetitively and constantly when your program is running. So sometimes your app will say, I need to ask something of the OS, I need to schedule something. So that call goes from your application code running in Java to the JVM, which is written in C++, I believe. That calls into the operating system. On Linux, it's written in C. And then that value returns through back to the VM and back to the application. And then just to be completely thorough and ridiculous, these calls also go all the way down to the computer sometimes in order to like read some value off of the network or something. And so each of these layers has a generally a negligible cost, and usually there's lots of techniques and tricks in these different layers to try and reduce that cost as much as possible. But there's also this sort of like impedance difference where the code running in the application side has a sort of view of the world that's different than how the JVM views it, which is different than how the OS views it, which is also different from the atoms in the computer. So when we talk about JNI, what we're doing is we're sort of like cheating, where we're running this system that's in two different modes. We have an application that's mostly written in Java, and then in our yellow box we have the C and C++ code for our application that sits directly on top of the OS. And so when we make a call in this world, generally your application code doesn't necessarily call your application native code. Instead, it actually passes through the VM first. And this is something interesting and not necessarily intuitive. So you say, I want to call some native function. The native function happens from your application code into the VM. The VM dispatches it into your native library. Your native library returns, and then it goes back into your application code. And this dispatch through the VM is necessary because the JVM has its sort of expectations as to how the world is arranged, and the native code has a different expectation. So a lot of this talk is going to be about understanding the consequences of these sort of different views of how what the program really is. So, and then again, ridiculously, if like you want to call native code to do something in the OS for you, it goes all the way through this entire pipeline. And so every single time you want to do anything, there's a lot of layers that things are passing through. So we've got our application, we've got this ARM code that we've written for it, and we're going to package it up into our APK file. And your APK file is full of tons of stuff. And when you introduce JNI, you have native code, not just for the platform that you're running on, but also the other potential platforms you may be targeting. So lots of different architectures that your APK gets big. So the architecture consequences mean that your application gets big, and you suddenly have to build without getting that full advantage of Java, where you can build for a single platform. When you're shipping native code, you have to build for every single architecture you care about. And one potential problem with this is that you don't necessarily know what architectures you're going to care about 5 years from now. And so if you're deploying apps, you have this sort of like ongoing cost of architecture. And you guys, everybody knows this because we all know this experience of like, hey, I want to go and play that old version of SimCity, and it doesn't work on this computer because x86 or something like that, or because Linux. So this architecture thing is a big deal, and JNI totally eliminates that benefit because we lose the ability to take our Java application and make it as portable as it had been. The other thing that's really a big deal about the JVM in Java is that it's garbage collected, and this is really like a nice developer feature. This makes us happy. We solve application problems and the runtime worries about allocating and freeing memory. Anybody who's spent a lot of time with C or C++ knows that most of C and C++ is mapping business problems to memory management problems. So we saw this talk about Kotlin, and we're like, holy cow, Kotlin is amazing. It's taking all these problems and it's making them go away. When Java was introduced, the feeling was exactly the same. It was like, wow, we don't have to think about memory management anymore. The garbage collector is magic, and it does all this work for us. And it was like really sort of transformational technology to have a system that's both easy to program against and also still that fast enough thing. Um, all right, so I'm going to talk about just what is actually happening in your heap. We're going to write some code. I've got 3 characters in my array list, and this is going to map to the following objects in my Java heap. So I have that array list. Inside of it, internally hidden, is an array, and each of those arrays point at the 3 characters. And sorry, characters was a terrible name. Each of the three people, and then each of those people has its own char array. And so this is how it feels logically, but physically on the machine, this stuff is arranged differently in the physical memory. And so when you say I got an array list, that array list is one part of your memory, and its internal array is somewhere else. And so the garbage collector is basically working with the memory allocator to figure out what is where. And when you have a reference to something, it's keeping track of where that is in physical memory. And the thing that's really interesting and unintuitive is that these locations are not fixed over time. So what could happen is your garbage collector could run, and it could try and compact and eliminate the gaps in this layout. So we may end up moving things around in the heap. And this is something that's completely impossible in sort of like traditional C++ types of models where values, pointers change. And that's why we call them references and not pointers, because pointers are to a physical location in memory, and references are to like a logical object. So we've got this set of objects that are constantly being sort of like sorted and rearranged by the garbage collector. And then in our application, we have both our Java objects, and then also potentially a whole bunch of native objects that are actually managed by the JVM, and also by our native code. So you think about taking your application heap and looking at it, you're going to see a bunch of Java stuff, and then a bunch of implementation details of the VM, your classes that you've loaded, all that infrastructure. And so when we're writing JNI programs, we're in this weird limbo where we have a foot in each side of the world. We have some of our code is worried about these the native part of the heap, the unmanaged heap, and some of it is worried about the managed heap. And the management of the heap is just the garbage collector going around and compacting things and getting rid of unused stuff. All right, so I'm just going to go through this and repeat. The garbage collector is managing and defragmenting the heap, and it's moving stuff around. And it's also keeping track of what references what. So if you think about writing native code that lives in the unmanaged heap, and you want to generally write JNI code that worries about Java objects, you're going to pass Java strings and Java values in. You have to worry about what happens when the garbage collector moves one of these things. And so when we think about how terrifying JNI is, it's usually because we're living in this gross hybrid world where values that sort of you never have to think about how they move in Java, and they never actually move in C++, but in JNI you live in the world where values do move and you have to think about them. So this is like one of the things that's like the fundamental stumbling block of JNI is that you're living in 2 heaps. And then I'm going to talk a little bit about fast enough and what fast enough means for Java and for JNI. Java is a language of abstraction. And what I mean by this is that we take these raw bits of our computer and really low-level primitives like pieces of memory, and we build models of it, and we build models of real things. We build models that solve business problems. And so you can see there's these different design decisions in Java where these models have sort of grown up and we've built them for each other. But the most simplest one is that there's this obvious implementation detail of Java lying around the list class and the array class. And so the array is this primitive building block that you use to bootstrap your array list. And once you've got your array list, you leave arrays behind. You're okay, we've survived this far. And there's just all these other things where Java's design is around abstraction. Methods in Java are virtual by default. So that means that every time you call a method, there's potential that it has to be dispatched using polymorphism. And there's also this strict encapsulation, which means that Java is also worried about making sure you don't run off the end of your array. It's saying, you want to read this piece of memory, I'm going to guarantee that that piece of memory is interpreted the way it's supposed to be. So we've got abstraction and our dynamic runtime, all these objects moving around, and the whole system is exposed to the application so that it can introspect itself. And so we're in this like really high-level Java universe, and we want to know like, why would you leave this to go to native code? Like, why are you so tempted by native code? What is it seducing you about it? And generally, we're seduced by native code because there's native libraries that do things that we can't do elsewhere. Good example is like you want to do SSL. You can't really do SSL in Java without either writing a ton of SSL code, as in JSSE, or by just talking to an existing native SSL implementation, like boring SSL. There's also things like Realm and SQLite, where we've got this really robust, very well battle-tested database, and it's much easier to talk to that through a native interface than to build up a brand new database in Java. And then I said PDF viewers because I didn't know if there were any Java PDF viewers, but it's the sort of thing where somebody's made a substantial investment in some technology in native code, and we want to get at it from Java, and we get at it from Java mostly because the code is there. And so we're going to native code because it's cross-platform. This is like the SQLite case because of a historical accident. You know, some system was built in native code a long, long time ago, and that's where it will be forever. Sometimes we write new code in native code because it would be inefficient in Java's performance model. And so earlier I was talking about this like system of abstraction and this memory safety. There are certain sorts of problems, generally pretty rare, that don't necessarily work very well in Java's performance model. It's like anything that's doing certain types of maths, for example, are inefficient in Java because we don't have a particularly flexible set of primitives. And we get benefits from access to fancy operating system features, and this is a really big deal. So if you're writing SQLite, you don't necessarily want to rely on the high-level abstractions over the file system that Java gives you. You may want to go right down to the metal and take advantage of very specific, maybe potentially operating system dependent library calls so that you can get the bits exactly onto the place in the disk where you want them with exactly the right latency and stability guarantees that you need. So blah, 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 native code. The thing I really like, this whole talk is like me just telling you never to use JNI, basically. A bad reason to use JNI is because it's faster. And so when we think about like, okay, JNI is this technology that unlocks all these C and C++ infrastructure, generally we don't want to use JNI because it's faster. And the reason it's not to go to JNI because it's faster is because typically the performance overhead of traveling between Java code and your native code diminishes the benefits that you get from using native code at all. So you write some function that concatenates two strings, and you say, I'm going to write this in native code. Well, ultimately what happens is the performance cost of going from the Java layer into the native layer, that the layer boundary eats up all the benefits that you get from the native code. And so one strategy that you'll often see when people are using JNI is that the JNI function calls are generally like, they're not very granular. You'll say, I want to decrypt this 2 kilobyte block using SSL. You're not going to say decrypt a byte, decrypt a byte, decrypt a byte, because every single call has this sort of non-trivial overhead. So again, just to keep hammering this home, we rewrote our program in C and it was 5x faster, or in Rust, or assembly, or Go, or C++. And the fact is that if you rewrite your program, it will probably be faster. You could rewrite your Java program in Java and it will be faster. So hammering on this performance issue, most programs are slow because they use inefficient data structures, algorithms, and abstractions. And Java has really good data structures, algorithms, and abstractions. So if you're thinking like, I want to sort some stuff, and I'm going to sort it in C. The sorting code will be the same in C as in Java. But if you want to write like a really sophisticated application, say you wanted to write a compiler or an IntelliJ, something really sophisticated, you'll find that the access to the high-level data structures and algorithms uh, outweigh any of the benefits you get from being sort of closer to the metal. Example of this is just like if you look at typical C and C++ programs, you'll see that they're typically written without like any interesting data structures. They don't use like anything bigger than hashes and trees, whereas in Java programs, we really have a very rich data structures API. So, all right, now that I've told you not to, now I've told you why not, I'm going to tell you how to do it. All right, so how to JNI? So there's this example that I whipped up earlier today, and the easiest way to get started into JNI is to take a working example and to customize it to your needs. There's a lot of boilerplate to getting a program running in an Android project and also to getting a JNI program running, and that boilerplate is definitely not something you want to write from scratch. You just want to steal it. And so I've got this like very trivial program that sends a string into native code, evaluates it, and sends it back, and I'll show you what that looks like. So I'm going to look at hello.java here. And so here's my function, load library JNI example. That is just boilerplate that we need in at least one place before we start interacting with the native code. And that tells the JVM to go and make friends with that corresponding yellow box in my diagram. It makes sure that that box is available. One caveat is that in current versions of Android, there's this really crazy, obnoxious bug where this call can crash if it's running while your application is actively being updated by the Play Store. And so there's an Android open source library, I forget the name of it, but you can use that instead, and it works a little bit more reliably. And then we have our native function called greet, and so this is kind of like an abstract method, but we're on a final class. And so the native here means this is going to be provided by C or C++ code. So that's our Java class. We just have a public static method. And now the corresponding C file looks like this. And this is, again, just a reminder of why we love Java. So you'll see that like there's a bunch of boilerplate up top. That big string in orange is fortunately generated for us by Android Studio. So you write the native function signature, and then in Android Studio will yell at you and say, I don't have this native function. And if you're lucky, you just alt-enter on it, and it creates the function for you, and you're very happy. And then we have this get string UTF-8 chars that takes the J string and converts it into a char star. And so when I was talking about the heap and how values are moving around on the heap, what this does is it pins down those chars long enough that it can actually read them. And so we actually get a copy of those chars that we can read while the heap is being moved around. And there are alternate versions of methods like this that let you alternate between copying the chars and pinning the memory. So if you want to say, GC, I forbid you from moving this string around, you can do that, or you can say, I just want you to copy these chars over for me. There are different sort of benefits to each. So we get those chars. We, in this case, I think we're pinning that memory. So we're telling the VM, you're not allowed to move this string. Native code is working here. And so we get that. Then we can actually read those chars. In this case, I say, if the string is string.equals Jesse, effectively, we're going to say yo dog. Otherwise, we're a little bit more polite. And then we release those UTF chars. And so basically, we're telling the VM, OK, you can move this string around in the heap again. GC, have at it. And then finally, I'm going to take my char star and copy it from the native heap onto the JVM heap with new string UTF. And so that all those functions that we just saw, there's a ton of them, and going into them in detail is a waste of your time and mine. But there's this relatively readable site that will explain to you what the functions are and how to get the things you want to get. All right, so that doc includes things like mapping Java types to C types. So you saw that I had a thing called a JString. There's just a dictionary that says, this is, if you want a Java long, this is what you get in C. It explains how to pin down references so things don't move around in the heap. It shows you how to call up into Java from C. So we defined a Java function that was implemented by native code. You can also do the opposite, where you're in native code and you want to call up into Java. And so you end up with my diagram where I've got my arrows going through the layers. You can actually go from native code up into Java and then back down. And there are occasionally reasons you need to do this. It'll tell you how to throw exceptions, and because you don't have things like the synchronize keyword, it'll tell you how to fake it out in native code. So you've decided that you're going to need to use JNI to solve some problem, some important advice. There's just so much better support in Android Studio than there's ever been for writing native code. If you looked at native code 2 years ago or even a year ago, the experience was abysmal. The tool chain was completely different, and you didn't feel like you were an Android programmer. Today it's much better. You can get Android Studio, it'll automatically build and download your NDK for you. It'll do things like let you navigate from Java code into the corresponding native code. And if you guys saw the Android Dev Summit, you can even do really awesome things like debug native code from Studio and step across the layer boundary. When you're using native code to call into Java code, ProGuard doesn't know that, and so ProGuard will happily delete functions that are only called by native code. So general rule of thumb is ProGuard is there to hurt you, and it doesn't leave you alone with JNI. There's an option on your emulator, and you can also enable it on your device, called check JNI, and this is just a feature of the runtime that makes JNI really, really strict. And because JNI is so dangerous, really, really strict is usually very good. So you can there's a doc on Google site on how to use that. Building JNI, again, is just so much better now than it has ever been. It builds with Gradle. Previously, you'd need to use a makefile, and you'd need to have your Java build and your native build, and then some duct tape to glue them all together. Well, today it's a lot better. You just use Gradle, and you can now test from Gradle on you can test from Gradle on your device, or you have to do extra work if you want to test your native code on a JVM. And this is not supported by any of the built-in tools. And the reason for that is mostly because your native OS is not necessarily known by the Android build tools. So if you're building on a Mac, the Android build tools know nothing about building Mac binaries. One more piece of advice, especially for right now, there are currently bugs in the way that the Gradle setup is working with JNI. They're working through them. But for now, you're going to need a separate Gradle module if you're testing JNI. So you'll have one module where your code lives, and then a separate Gradle module where your tests live. They're going to work through that, but in the interim, something to be sort of careful of. So that's it. Basically, this is how JNI works. Don't use it, and here's how.